Okay, inverse relations and functions. Oh, yeah, fun facts. I went down to Arizona over spring break and just saw all these cool dinosaur prints. And these right here are like human footprints, and these are dinosaur footprints. And I don't know, draw your own conclusions. The guy was trying to tell me that the dinosaurs were around during the humans, and I don't know. I'm obsessed with dinosaurs, and this was just blowing my mind. Other fun fact, Carbon High School, where I went to school, Carbon, we were the Carbon Dinos. Probably a big reason why I'm obsessed with dinosaurs. But anyways, yeah, we had like this T-Rex statue in the commons area. It's kind of fun. Anyways, okay, so enough about that. That has nothing to do with this. So functions versus relations. What is the difference? So if you think about the relationship between two quantities, so we can think about like when you learned functions, you probably looked at like a little machine or something. There's a lot of times teachers will show this video of like you put something into the machine and you get an output. So like if you put in an elephant, you get out a mouse. Like that's weird. Like what is going on in the middle of this machine? Or like you put in 2 and you get out a 4. You put in a 7, you get out a 34, whatever it is, okay? Now, the difference between a function and a relation, they all have to do with inputs and outputs, but for the function, there's only one output for every input. So everything we put into this function machine, you only get one output, okay? Versus a relation where you can put in an input and get out multiple outputs, okay? So here's a graphic that shows it pretty well. So like here, the P goes to the M. The Q goes to the N, and the R also goes to the N. Now, all of these inputs go to only one output over here. So this is a function. An input, so these two inputs go to the same output, but that's okay. All right? This one is easy to see. So we have P goes to X, we have Q goes to Y, we have R goes to Z. Each input has a unique output, okay, because they're all different. If it has a unique output, this is called a one-to-one function, which we're going to go through in just a second. But so this one is a function. Whereas this last one, so P goes to X, Q goes to Y, and Z. So this input goes to two outputs over here. Which means, so if I put Q into here, and I get out Y and Z, that is not a function. This is just a relation. So every function is a relation, but not every relation is a function. Okay? All right. So a relation is just any ordered pair. So if we have, to find the inverse of a relation, so say you're given all these points. These are just ordered pairs. All you have to do is flip them. So the inverse of 1, 2 is 2, 1. 2, 6 is 6, 2. 4, 9 is 9, 4. 5, 13 is 13, 5. 6, 21 is 21, 6. 7, 33 is 33, 7. Okay, you just flip them. And then, so let's do an example. So if we're given this relation and we want to find the inverse, well, I can just flip-flop these, okay? So our inverse is going to be negative 7, 0, 2, negative 1, negative 2, negative 4, and 3, 6. This negative 1 part right here, this means the inverse of R. I'm going to go through notation in a second, but this negative 1 just denotes an inverse, okay? Easy peasy lemon squeezy. All right, one-to-one functions. What does that even mean? I kind of talked about it before. It means that for every value of x, there's a unique value of y, or f of x, whatever you want to think of it. Okay, so for every value of x, we have a unique value for y. So if I look at these two, so the green one here, well, this one's easy to see because like 4 goes to 3, 2 goes to a negative 1, 0, 1, 2, 3, 4, 5. They all have a unique value, and I could go backwards. Okay, I could go both ways here. Now in this one, the negative 4 and the 4 both go to 16. So I have two inputs that go to one output, which is okay if I'm just trying to see if it's a function. But if I'm trying to check if it's one-to-one, since these two inputs go to the same output, that means that this is not a one-to-one function. Because if I was to take 16 and go backwards, I'm going to end up at 2 points there. Okay? So that is not one-to-one. A function has a one-to-one relationship if the relation and its inverse are functions. Okay, so they both have to be functions going in both directions. Okay? Okay, so vertical line test, you have learned this before, but remember that the vertical line test tells us whether or not a function is a function. Like this one, for example, it crosses at these 2 points, which means that this is not a function. Okay? Now, so if the vertical line test tells us whether our function is a function, or whether our relation is a function, the horizontal line test is going to determine whether the inverse of a relation is a function. So say that we have like the y equals x squared graph. Okay, so that looks like this, right? Well, if I do the vertical line test here, definitely a function. It only crosses once. But if I do the horizontal line test, it hits at those 2 points. So that means there is not a inverse here. Not. I'm going to put no inverse. Okay, and that would be the same for like the absolute value of x. So if I had the y equals absolute value of x, that graph looks like this. That will not cross past that test. Okay, but then if you had like the cubic, so like y equals x cubed, well, that just looks like this. That passes this and this, so that is a one-to-one function, which means it has an inverse. Okay. So both the relation and its inverse must be a function in order to be one-to-one. Now let's look at this. So if you're given a graph and you have to determine whether it's a one-to-one function, do the vertical line test, passes, yep. Horizontal line test, passes. So that means yes, this is a one-to-one function. Okay, if we do this one, so this is like a cosine curve. It passes the vertical line test, so that means it's a function, but then is the inverse a function? No, because it's going to hit this line there, 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 and there. And it's going to continue to just hit it all the way along this thing. Okay, so that means that this is not a one-to-one function. Okay, inverse functions. So the notation for an inverse is f to the negative 1 of x. That is the inverse. Inverse of x does not mean 1 over f of x. This is the reciprocal. Whoa, sorry, my pen is like reciprocal. Okay, that's the reciprocal. So not all functions have inverse functions, like we just talked about, like the squared graphs, okay? So to find the inverse, you're going to replace f of x with y. You're going to interchange x and y, solve for y, and then rewrite y as f inverse of x, okay? So first we're going to determine if f of x has an inverse by graphing it. If yes, then find the inverse and state the restrictions. So we have f of x equals 4x minus 8. If you have a graphing calculator, just pull it out and do it on there. If not, you can go to Desmos.com. I feel like I've talked about Desmos before, but that's an online graphing calculator. It's great. So then here we have that. This is a one-to-one function. It passes both of those. So that means I can switch my x and my y's. Well, first, let me go back. I'm going to put y in for f of x, and then I'm going to switch my x and my y. So this would be x equals 4y minus 8, and then I just need to solve for y. So add the 8, divide by 4, and I get f inverse of x equals x plus 8 over 4. And I graphed this over here on the right. It's that blue line right there. And then notice, if I was to fold right along that line of y equals x, they would fold right on top of each other. That is how we are going to verify this stuff next time. Okay? Let's do this one. So f of x equals 1/2 x cubed minus 1. Graph it, it looks like that. Now right here, it looks like if I draw a horizontal line, it might touch at multiple places. It is not going to. If you zoom in really, really far right there, it doesn't actually, like, it's more like this. Like, it levels off a little bit, but there's no points in there that are the same, okay? So then that means it's going to pass both tests. And I can change my f of x to y and find the inverse. So we have x equals 1/2 y cubed minus 1. And I know I messed up my notation here, so I'm just going to do it by hand. So I can add the 1 over, so I have x plus 1 equals 1/2 y cubed. To get rid of that 1/2, I'm going to multiply both sides by 2, so I get 2x plus 2 equals y cubed. Then I can cube root both sides. So I have y equals the cube root of 2x plus 2, which means the inverse here equals the cube root of 2x plus 2. Cool? Blah, blah, blah. See, I made it an x right here. Whoopsie. But this is the right answer. Okay? So then if I graph that, it looks like that. Discard. It looks like that. And that does reflect over that line. Okay? This one, so x minus 4 squared plus 6. Now, anytime you see this squared, you should automatically know there is no inverse unless there's a restriction on the domain, which we'll do in just a second. But if I graph this, I get that. It passes the vertical line, but not the horizontal. It is hitting at those 2 points. And so that means it is not one-to-one. There's no inverse. That is an easy problem. Okay? Nope, says Kanye. Okay, so then this one. So f of x equals 5 over x minus 8. It looks like that. And it has a asymptote here at x equals 8. And if you remember back to like December when we were doing this, that is because the bottom of this fraction can't equal 0. You can't divide by 0. So if I plug in 8 for x, I'm going to end up dividing by 0. Which I can't do. So that means our restriction is x can't equal 8. Okay, but this does pass both tests. So I can find the inverse. So I have y equals 5 over x minus 8. Switch my x and my y. Multiply by y minus 8 to both sides. Distribute that x in. So I have xy minus 8x equals 5. Add the 8x. So I have xy equals 5 plus 8x. And then divide by x. So I have f inverse equals 5 plus 8x over x. And this time my domain is restricted, so x can only be greater than 0. Or x can't equal 0, my bad. Okay? And that graph looks like that, which looks a little weird to see, but if we put that line in, it's easy to tell that if you fold over that line, they're going to go right on top of each other. Okay, last one. So 3x squared minus 1. If you were to graph this, and I'll graph it in a second, like with the decimals, but 3x squared minus 1 looks something like this. Okay, it's down here. That's our vertex at -1. But if we have this restriction here of x has to be greater than or equal to 0. So that means I am going to ignore the entire left side of this. And I'm only looking at the right side of this graph because now I have just created a one-to-one function that I can find the inverse of. Okay, so it's that function there, which I can find the inverse of. So the domain is restricted. So then I'm going to find my inverse. So y equals 3x squared minus 1. Switch the x and y's. Add 1. So x plus 1 over equals 3y squared. Divide by 3 and square root both sides. Now, when we square root, typically you would do a plus and a minus, right? But since our domain is restricted to the positive x's, I'm just going to do the positive of the square root. Okay, if this was restricted to the negative x's, I would have done the negative of the square root. Cool. So we only use the positive part because the domain is restricted to positive values. Okay, so then there is my inverse, and it does reflect over that line. Cool beans. That's it. Baby Yoda says bye. Whoops.